Hey guys, so I'm going to go over the sheet from Friday, the practice sheet. So here we go. All right. Okay, so number one, a compound is found to be 25% hydrogen and 75% carbon by mass. What is the empirical formula? All right, so we can't use calculators here, but we can still do this, and we should go do this some mental math here. All right, so 25 grams of H. All right, we know H has a mass of 1, so we're going to have 25 moles of H. All right, carbon, 75 grams. Carbon has a mass of 12. 75 divided by 12, right? Well, 6 times 12 is 72. So it's going to be something around there. And go a little bit further, we got 3 left over. So 3 of 12 is a quarter, so 6 and a quarter. Right, so little mental math there. All right, and then we're going to divide by the smallest. So we would have 25 over 6.25, and that's 4. And 6.25 divided by 6.25 obviously is 1. So the ratio is 1 to 4. The only one that fits that bill is D, so the answer is D. Okay, 2. Which of the following shows you how you can determine the number of molecules in 50 milliliters of mercury? Mercury has a density of 13.6 grams per milliliter and a molar mass of 200.59. Right, and then we're not going to write any unit cell, and we're not going to write any of the number ones. And we just want to pick out which one works best for this. So obviously, you could just write it out and then match everything up. But you kind of want to think, what are we going to start with? We're going to start with 50 milliliters. We need to start with that. That's our starting amount. And if we look at B already, 50 is not up top, so it can't be B. Right? So we want to start with 50 milliliters, and then we have to go from milliliters to mass, so we have to multiply it by its density, which is 13.6. So let's just take a quick look. Up here, 13.6 is being divided. That's actually not going to work, so it can't be A. C so far looks good, and D also is dividing it, so already we can just say it's C, right? Because it can't be any of the other ones. So again, you could write the whole thing out, but see, you can kind of figure it out step by step to try to keep moving and keep a good time up through the problems. All right. Okay. So we have some M plus. It's an unknown metal with a charge of +1s, an alkali metal. Probably alkali metal, not necessarily sure. Positive, like copper. See this example. Anyway, a student dissolves the chloride. So we get MCl, this unknown chloride, and we make 100 milliliters of solution. The student mixes the solution with excess silver nitrate in order to produce the precipitate silver chloride. The precipitate is dried several times and a constant mass has been achieved. The following pieces of data are available. Use this information to determine the compound MCl, right? And so we're going to kind of go from there. So just like before, we've lost all of the water. So we kind of want to find out, hey, what do we have left over? And then we're going to kind of go from there. So we, at the end of this, turn my pen back on. Okay, have 2.23 grams of filter paper and silver chloride. That's dried silver chloride. So if we want to find out just how much silver chloride is there, we're just going to get rid of the filter paper. Right? And this is going to give us 1.43 grams of silver chloride. Okay? So again, we knew the silver chloride was 2.23 with the filter paper. It's all dry. So we just got rid of the filter paper's mass, and that's how we found out the mass of silver chloride. Okay. We're given the molar mass of silver chloride. So we want to turn this into moles. We're just going to divide this by its molar mass, which is 143. And you don't need a calculator for this. That's just 0.01 moles, okay, of silver chloride. Okay. Every item or species in this reaction here has a charge of +1. So that means all of the mole ratios are going to be 0.01 as well, all right? And since we have excess silver nitrate, that means if we have 0.01 moles of AgCl, we actually have 0.01 moles of MCl. They have to be the same. So now we can kind of think back to our formula here. N equals M over capital M. Well, what do we know? We know our moles is 0.01, and we know the top end, the mass, how much mass is? 0.74. So we can rearrange this equation right here to get the molar mass. All right, so that'd be 0.74 divided by 0.01. Right, this is common math you're gonna ask people to do in this class without a calculator. We're dividing by 0.01. We just moved the decimal 2 places, and we're actually gonna get larger. We divide by a number less than 1. The overall number gets bigger. We get 74 grams per mole. So now we just have to work backwards. Hey, which of these has a mass of 74? And potassium chloride does. Chlorine is 35, potassium is 39, 39 and 35 gets you 74. So that is number 3. Okay, 4. The mass percent of glucose is 40% carbon, pure glucose, 40% carbon. And we have a sample and it's only 38% carbon. So we say, hey, why do we have less carbon than we think? So which of the following impurities is going to cause that? So let's kind of look here. So water definitely would cause less carbon to be present because there's no carbon in water. So this is plausible. So I'm just going to check mark here because it's plausible. Let's just go through everything else to make sure, see if it's the best answer. Okay, so we look at ribose, and if we look at ribose, ribose only has 5 carbons to it. And glucose has 6. So we would think that ribose would also contribute to this decreased percent mass of carbon. However, if you look at ribose more carefully, the ratio is the same as glucose. It's 1 to 2 to 1. That is the empirical ratio for glucose, same thing for ribose. So ribose actually will not change the percent. It would actually keep it at 40. So ribose does not work. Fructose, an isomer of glucose. Isomer just means same exact elements involved, just a different layer or a different structure. Well, because it's the same amount of carbon as before and it's the exact same thing, it definitely is not fructose. All right, sucrose. So sucrose actually has more carbon in it. And if we look at the other two numbers also increased, but the ratio actually increased less than 2-fold. In sucrose, if there was excess sucrose, our percent would actually be greater than 40 because sucrose has a percent mass of carbon larger than 40%. So sucrose also doesn't work since our percent went down, so it must be water, and that's why it went down. Right? And even this one right here, how many grams of hydrogen are contained in 96 grams of methanol? All right, so we got 96 grams of methanol. We need to find out the molar mass of methanol. Carbon is 12. Each H is 1. 3 plus 1 is 4. 4 plus 12 is 16. Another O is 16. That's 32 grams for 1 mole. And that's 3 moles. Okay. So 3 moles of methanol. Okay. Well, if we look at this, for every 1 mole of methanol, we have 4 moles of H, right? 1, 2, 3, 4. So in 3 moles of methanol, we actually have 12 moles of hydrogen. And if we want to know how many grams of hydrogen there are, well, since hydrogen has a mass of 1, molar mass of 1, 12 moles equals 12 grams, and the answer is C. Okay, 6, mass spec. So based on the graph below, what is the average atomic mass? So again, no calculator here. So let's see how we can estimate this problem through. All right, 50% of our item comes from 90. So we can kind of think, right, 0.5 times 90. That means the remainder has to be 50%. So let's kind of just look at these two things. These two lines are basically the same, and they're both 1 apart. So we can think that's basically all at 93. It's like the height of both those put together averages to 93. Okay. We have something down here at 91, and we have something up here at 96. Okay. Looking at these two things, all right, my estimate would be that these two are going to basically kind of come and make this line like a new line right around almost next to the 91, a little less than 91, right? Those two would average together. So now we have a big line at 90, okay? We have a 93, that's that other huge line, and I misspoke. And then this other one is gonna be like just before 93, like, I don't know, 92.8. It doesn't really matter. Okay. So now looking at these, right, which one of these makes the most sense? Well, we know 50% of it is 90, and basically 50% of it is a little less than 93. Well, if we found the average of 90 and 93, that's 91.5. But since not all of it is 93, some of it is a little less than 93, it's going to be a little less than an average of 90 and 93. So the best approximate mass is 91.4. And that is your multiple choice questions. Okay, so we're going to solve now the 3 FRQ questions. Okay, so number 1, a hydrocarbon is composed of just carbon and hydrogen and is combusted in the presence of oxygen. The reaction produced 24 grams of water vapor and 44 grams of CO2. What is the formula for the hydrocarbon? So our hydrocarbon starts out looking like this. And using the laws of conservation of mass and mole ratios, we're going to work backwards from our products to determine what X and Y are. Okay? So if we look, 24 grams of water vapor, well, that water vapor is where we're going to get our hydrogen from. So we know that there are 18 grams of hydrogen in a mole of water vapor. We don't really care about the water vapor. We want to know how much hydrogen is in that water vapor. Well, for 1 mole of H2O, there are 2 moles of hydrogen. So now if we solve 24 times 2 divided by 18, that gets us 2.67 moles of hydrogen. So we're going to do the same thing for the carbon dioxide. We have 44 grams of CO2. The molar mass of CO2 is also 44 grams. So for every 44 grams, we get 1 mole. And the ratio in CO2, for every 1 mole of CO2, we also get a mole of carbon, right? It's a 1-to-1 ratio, 1 C and 1 CO2. So 44 divided by 44, that gets us 1 mole of carbon. So now we know our moles, we know our X and Y values. Now, we could try to write it like this, C1, H 2.67, but that's not acceptable. You have to get whole numbers. Okay, so what we could do to do that, we basically just have to multiply by some number to get to a whole number, and just start going through your integers. The closest integer that's going to fix that for us is 3. And if we multiply by 3, we get C3H8. And there is our answer for number 1. Okay. Number 2, Epsom salt, magnesium subhydrate is heated to 250 degrees Celsius. And then all the water is evaporated. The sample had a mass of 1.687 grams initially, and after it was heated and cooled, the mass fell to 0.824 grams. What is the formula of the hydrodiversion of the Epsom salt? So similar to the problem we did earlier today, right? We basically want to find out how many moles of magnesium sulfate do we have and how many moles of water there were, and then compare and find a mole ratio. Right? So let's kind of see what we've got. We know that there's 1.687 grams to start with, right? And then afterwards, so this is the magnesium sulfate and the water mixed together. And then after heating, our new mass is 0.824 grams. So we started with magnesium sulfate and water, and then this is after heating. This means this is just the mass of magnesium sulfate. And if we subtract this, 1.687 minus 0.824, we get 0.863. Well, that's how much water left. That's our mass of our water. Okay, so again, this is what we started with, which is the magnesium sulfate and the water. This is after it was heated to, so the mass fell to this value. So that means the only thing left here is magnesium sulfate. So that's how that is. Which means that what left, if you subtract this, is the water. So now we'll quickly go to moles of each. Right, 0.863 divided by 18, 0.0479. Okay, and then for this one, magnesium sulfate, molar mass, magnesium's 24, for oxygens is 64, sulfur is 32, so 24 plus 32 plus 64, get 120. All right, so 0.824 divided by 120 is going to be very small, 0.00687, right? And now we just have to find our mole ratio, right? We want this in terms of magnesium sulfate. How many moles of water per magnesium sulfate? So we do 0.0479 over 0.00687. And this gets you 6.97, which rounds up to 7. So the formula is magnesium sulfate 7 hydrate, or heptahydrate. Okay. 3, rust comes in 2 forms, iron 2 oxide and iron 3 oxide. A sample of rust is analyzed and is found to contain 75% iron by mass. So that's what we know. So question A, if the sample is only composed of both forms of rust, meaning the sample just has iron oxide, Fe2O, and Fe3 oxide, iron 3 oxide, is that possible? Justify your answer. So we should just do real quick, hey, what's the percent mass of iron in both compounds? Right, so once we know the percent mass of iron, we can find out how this answer stacks up. So for iron oxide, that's 55 over 81. Iron's 55, oxygen 16. And for iron 3 oxide, we have 110, and then 110 plus 48 is 158, right? And we'll multiply them both by 100. And then let's see what we get. So 55 divided by 81 times 100. This is 67.9%. And then 110 divided by 158 is 69.6%. Okay, so even if the sample only contained iron 2 or iron 3 oxide, Fe2O3, like it was 99.999999999%, this one, it still can only have a max percent mass of iron of 69.6%. So the fact that we found it to be 75%, is this possible? No. There's no way it's made up of just Fe2O3 and FeO. if the percent mass is 75% iron. There must be some impurity in there that has a much higher iron count by mass. We don't need to find it, it doesn't ask us for it, but that's how we can justify our answer. All right, B. Some solid iron is ground into a powder and placed in a vessel with some halogen gas, group 17, fluorine, chlorine, iodine, bromine, right? And a reaction occurs, and the compound FeX3 is produced. The compound is 49% by mass iron. What is the formula for said compound? All right, so, all right, again, we're going to use our what we know about mass percents. We'll go with this red color. All right, so we got 49% iron by mass. So we can just assume we have 100 grams, right? So if we have 100 grams and 49% of it is iron, that means we have 49 grams of iron. That's a hideous color. I don't like that at all. Sorry. No. Go back to that fun pink one. There we go. All right, 49 grams of iron. All right, well, we can find out how many moles that is. Iron is a molar mass of 55 grams, 1 mole. All right, 49 divided by 55 is 0.8909 moles of iron. All right, well, if we want to find out what this X3 is, we're going to just kind of think backwards. Whenever we want to find out what that mole thing is, let's think about molar mass. N equals M over M. All right, so let's see how we can get there. We're trying to find molar mass. So we need to know mass and moles. Well, we're going to get both right from the problem. In fact, we know the mass. If 49% by mass was iron, that means 51% by mass was this other compound. So if we have 100 grams, 51% is 51 grams. Don't mind that weird line through there. All right, we're looking for the molar mass. Moles. Well, we're going to use the mole ratio. For every 1 mole of iron, we make 3 moles of X3. Or X, whatever X is, we have 3 of them. So I'm just going to multiply this real quick by 3. So 0.8909 times 3, that's 2.67. So that's our moles. So now we have this, 2.67 equals 51 over M over molar mass. These trade places. So the mass is 51 over 2.67. And you get 19. And if you look on the periodic table, who has a molar mass of 19 in group 17? Fluorine. So what's the compound? Iron fluoride. All right. So guys, that's the problems for today. Good luck. If you have any questions, let me know.